Thank you for the introduction, and I apologize for the mouthful of a title up there, but it kind of contains everything that I try to talk about today. I want to start by acknowledging the work of two of my students, Dominic Cadelti and Austin Goodrich, that have worked on this problem over the years, and also acknowledge the support from NASA, NSF, and the 22 CTR summer program. So I'm going to talk about immiscible interfaces, and my focus is on atomization, so spray generation. And so here is an example of a simulation we did some time back of a turbulent liquid jet injected into compressed stagnant air. And what we observe in terms of the breakup mechanism is that liquid turbulence creates the initial surface perturbations. You see that here after the injector exit. There are the streaky structures that are in the wall boundary layer that get after a while imprinted on the liquid surface that cause corrugations. And then those perturbations are stretched into ligaments due to shear and acceleration. And then those ligaments break due to capillary forces assisted by additional corrugations imposed by turbulent eddies in the vicinity. And you can actually generate quite a broad range of drop sizes from this primary breakup alone. So much so that in many of our simulations, and now in some experiments as well, there's actually not much secondary breakup happening. That the initial drop size distribution seems to be set by this initial breakup mechanism through ligament formation directly. The point here is that surface tension forces that occur on the small scales are important for atomization. So we want to do LES because these DNS or highly resolved, they're not really DNS, highly resolved simulations are very expensive. So we want to go for an engineering application, so we want to go towards LES. And traditionally in single phase LES, you rely on a cascade process. Basically that you can infer the subfilter dynamics from the resolved scale dynamics of your flow field. And then you have molecular viscosity that ends the turbulent cascade at the Kolmogorov scale. So the question is there something similar for liquid-gas phase interface dynamics? So traditionally, surface tension takes the role of viscosity, and it limits the smallest interface corrugation to the so-called Kolmogorov-Hinze scale. So in that sense, surface tension can be thought of as a dissipative mechanism for surface corrugations. But as we've just seen, surface tension, when you have ligament formation in primary breakup, actually generates small-scale structures, small-scale drops. So what surface tension does depends on the surface geometry. Surface tension can destabilize the surface through the Rayleigh plateau mechanism, or it can stabilize it if you have a more flat surface or you already have drops or bubbles generated. So my point is that the effect of surface tension depends on the local interface geometry, and it's that local geometry. So if we want to do LES, and pardon these cartoonish figures here, let's look at two scenarios of a fully resolved geometry. So we have a sheet here, and we have a ligament, and we know that surface tension in these cases here tends to stabilize the interface, so we don't have any breakup. In these ligament cases, we have surface tension that destabilizes the mechanism, and we have breakup. So we want to do LES. So let me filter this geometry using a standard volume filter. So I filter this on the left, and I filter this geometry on the right, and lo and behold, I have the same filter geometry for this specific case. But I know that on the subfilter scale, the dynamics are very, very different, but on the filter scale, they express the same way. So what to do? Well, I'm kind of saying that I cannot always infer the subfilter interface dynamics from the filtered scale alone, especially in atomization scenarios. So maybe a different modeling approach is needed for this. And but we're doing in the end still LES. So here's my one slide summarizing the governing equations. So basically what we do, we filter the momentum equations. We kind of follow the approach by Touton. And so if we do this, we get subgrid terms due to subfilter acceleration, viscous effects, surface tension, and momentum transport. And if you look at these terms, the more traditional single phase one is this one here, only the momentum transport. But because we have surface tension, we get these additional terms. And because our interface on the scales that we're looking at is a discontinuity, we also have these acceleration terms that come through the jump in density and the viscous effects due to the jump in viscosity at the interface. And then we need to keep track of the position of the interface. Different approaches we could use. Here we're using a capturing method, so we use a volume fraction equation. You have to filter that, and that introduces subgrid terms due to subfilter interface transport. And if you're in a low Mach number flow, the velocity fields are solenoidal, so incompressible, then the divergence field is zero of the velocity and this term drops out. So the traditional approach is to try to come up with models, closure models for each one of these terms, inferring from the resolved scale what happens on the subfilter scale. But as I try to point out, that might be a bit tricky for atomizing flows. So here's the alternative approach, the dual scale approach. We introduce a fully resolved interface geometry on a, let me call this DNS scale, although DNS with two-phase flows is a nebulous term to begin with. Let me say a high resolution mesh. It's a auxiliary mesh that's just overlaid on top of it. We use a refined local surface grid method, and this DNS scale mesh exists only in a narrow band around the fully resolved interface. Technically, we would need it only at the interface, but because we do a capturing approach, we have to do this in a band around the interface. And what's important is we can independently load balance that for parallel efficiency. So if you have a fully resolved realization of the interface, you can theoretically close all of these terms here that appear in the filtered equation by just explicitly filtering the fully resolved realization. No free lunch though, because the model task then shifts from trying to maintain that fully resolved realization with the information that you have available. And the information that you have available is the filter scale velocity. So the fully resolved interface advection equation is this guy here, where you know the filtered velocity. So what you'll need is now a model for the subfilter velocity, not everywhere, but just the subfilter velocity on the interface itself. So for us, in a narrow band around the interface. So sometime back with Mikhail Gorokhovsky, we came up with this model that we split the subfilter velocity, the subgrid velocity, into separate terms that we just linear superpose. We have a velocity contribution due to subfilter surface tension forces, due to subfilter eddies, subfilter shear and acceleration, and a contribution due to subfilter phase change if the interface moves, propagates normal to itself relative to the background flow. So let's start with this one here. The subfilter surface tension force velocity. It's a quantity that I need at the interface. It's an interfacial quantity, so in a Eulerian formulation, I have to move it with the interface. So this portion here just moves this velocity with the fully resolved velocity, attaches it to the interface. And then the change of this surface tension induced velocity, I'm going to model following essentially a Taylor analogy. So I'm going to treat surface tension as a spring. So imagine you have a single filter volume cell here, and you have like an ellipsoid of an interface. If you would filter this geometry, you're left, if it's within a single filter volume, you're left with one mean curvature value. And think about that one mean curvature value, the equivalent geometry would be that of a sphere or a circle in 2D. So you will have regions where your resolved curvature is higher than the filtered curvature, and region where it's lower. So I'm going to treat the extension of the spring as that difference of the resolved curvature and the filtered curvature in the direction of the filtered normal. In the direction of the resolved normal of the interface. And then the spring constant scales with the surface tension coefficient and the filtered curvature as well. So that's my spring acceleration, and then the damper is due to viscous forces proportional to this subfilter surface tension velocity, and with scaling arguments you get the viscosity here and the length scale squared. Okay, so how does that work? This is a simulation of a single LES filter volume, so single point LES. Nothing happens on the filter scale because you only have a single point. So the entire dynamics here of this oscillating drop are on the subfilter scale, calculated from this model velocity. And if you compare that oscillation period to the theory over different radii, you get quite good agreement between the model and the theory. The same thing works for ligament breakup as well. Just as an example, again, a single LES cell, so all the dynamics happen on the subfilter scale. If you perturb this cylinder here, certain wave numbers, and you modify the radius, you get scenarios where you would expect a single drop due to Rayleigh plateau breakup. And in this case here, you would expect 2 drops, and I just let this run, visualization of that subfilter velocity. And you'll actually, that's what the subfilter model will do as well. Get 1 drop here, you get 2 drops. So those dynamics from the model on the subfilter scale due to surface tension, we seem to be able to capture quite well. The next component I want to talk about is subfilter turbulent fluctuation. And we generate those fluctuation velocities on the fly using a spectrally enriched differential filtering approach, the SDF method by Bassen. Just brief summary, you recursively refine your velocity using as a first step an approximate deconvolution, and then you use spectral enrichment here to fill in the scales that you have refined. And you do this all the way down to your fully resolved mesh scale. And this here, the K is the local kinetic energy, and Ji is a normalized vector that models the structure of the subgrid scale motion relative magnitude of each one of the velocity component. The point of this is that this is not a purely random velocity field. It takes structure information from the resolved scale into account. If you do this with the SDF method, and here is an example, homogeneous isotropic turbulence. Here is our filter scale, DNS in the black line. If we have the LES cutoff scale here, and we use that SDF reconstruction, you get a negative 5/3 energy cascade without any viscous subrange. But you can get the viscous subrange, this impact here, if you adjust the coefficients in the spectral enrichment on the fly. So I'm going to show you results with both of these in a second. So first verification test case, homogeneous isotropic decaying turbulence. This case here is RE lambda 156. We did RE lambda of 313 as well. Essentially the same type of result. No gravity, unit density and viscosity ratio, to keep it simple at the beginning. We put an initially planar interface into the decaying homogeneous isotropic turbulence field. Here's the data of the DNS flow solver resolution. The flow solver is NGA. Well, if we're using it as an LES model, we have a dynamic Smagorinsky single phase LES model. And the overset mesh, if we do this here with 32 resolution for the LES, the overset mesh goes down to the DNS resolution of 512 kilo, locally around the interface. Okay, so what does this look like? This is the case, no surface tension. Here, the DNS, you see these highly corrugated interface. If there's no surface tension, there's nothing limiting the appearance of small-scale structures of the interface. It will be surface tension that provides the cutoff. And this is the corresponding fully resolved SDF interface. So I'm going to show you 3 metrics here. First one is the surface area density. So what you do is you go normal to the initially planar interface and calculate the area density averaged in normal in planes normal to the normal direction. the PDF of the absolute value of curvature, and the WOF covariance spectrum at the midplane. And the dashed lines are always the DNS, and the solid lines are the dual scale results. When you see the case for infinite Weber number, we get the curvature statistics quite well. We're under predicting the surface area density here, and the WOF covariance spectrum is not too bad either. Let's introduce surface tension. So Weber number, based on the Taylor microscale of 8.8. We get much better agreement on the surface area density. There's this shift in the PDF of curvature because you're starting to filter out, due to surface tension forces, the high curvature values. If I introduce even more surface tension, you directly see this DNS versus SDF, right? That the interface has much less small-scale corrugations. That's reflected here in the PDF of curvature. And we start to get the covariance spectrum in the midplane very well as well between DNS and SDF. Here's just a snapshot to do the comparison. And I can introduce even more surface tension. And the agreement generally remains quite good. Now, the important part is this. If you look at this here, this is our subfilter scale from here on out. That's the LES filter scale. So this impact of essentially the Kolmogorov-Hinze scale, that if you increase surface tension, you filter out, you take out small-scale corrugation. In this case here happens in the LES entirely on the subfilter scale. So it's entirely has to be reproduced by the model, and the model is able to do that quite well. Okay, the next thing I want to talk about briefly is the subfilter phase change. So basically, you can think about that two different ways. In the context of liquid gas flows, this would be evaporation. Well, it could be condensation as well, but we'll look at it as evaporation. And we are going to borrow ideas a lot from combustion, premixed combustion. So you could think about this as well as a premixed flame front that propagates with a burning velocity SL. That's why there's this terminology of SL. But for us, it's an evaporation front, and there's an evaporation speed SL. The simplest possible model you can do on the fully resolved scale is to just assume that that evaporation speed is constant to see what the impact is on the surface dynamics. You can go with a Markstein type correction if you wanted to as well, or you can do some improved model using the local field temperature or composition. I'm going to do with the simplest model first here. Same type of setup here as before, planar interface, but now we're going to have normal propagation of the interface in there with different strengths ranging from scaled with U prime 0.17 to 1.7. No surface tension here initially, lowest SL value, highest SL value. And what you'll see is the effect of kinematic restoration. That's a term from premixed turbine combustion as well. So the interface propagates normal to itself, reconstructs itself, takes out fluctuation due to kinematic restoration. That is, here's just a look, but in the interest of time, I skip over this. If you look at m dot over m naught, you can see Darm-Köhler's relationship here. You get consistent results, obviously, from the DNS. If I look at the interface from the liquid side, and the same interface from the gas side, you'll see this typical behavior that you see rounded structures, more rounded structures on, if you look from the liquid side, and you see very peak ridges from, if you look from the gas side. Huygens principle basically is at work here. So that's reflected in the PDF of curvature as well. That's no longer symmetric. So if you increase the evaporation speed, that asymmetry increases at early times and at late times as well. Okay, so can the dual scale model reproduce these DNS results? Okay. So here I'm going to look at two cases, the low evaporation speed case and the high evaporation speed case, the PDF of curvature. If you just use the SDF method to reconstruct the negative 5/3 spectrum, you'll see that you're quite a ways off. So it's important that you get the small scale kinetic energy right. So if we use the SDF method, adjusting the coefficients to get the initial time step kinetic energy spectrum correct, we get reasonably good agreement. In the low evaporation case, quite good agreement on the high evaporation case. We keep these coefficients now constant. We don't adjust them, although the turbulence decays. And if we step through later times to the final time, you'll see that we get astonishingly good agreement between the DNS and the statistics of the dual scale interface in terms of the PDF of curvature. Okay, conclusion and outlook. I showed you a little bit background here. On the dual scale model, we are able to reproduce the Kolmogorov-Hintze scale effects if they occur on the subfilter scale, and you can add additional physics to it. The next step would be to add surface tension to these evaporating cases. These are just DNS results. And there's actually something interesting happening. You get these ridge lines that form due to Huygens principle. Evaporation then evaporates through these thin sheets, leaving behind ligaments that then break up. So in some sense here, in this case, if you look at this closely, evaporation enhances the breakup of those forming ligaments that then cause breakup. I typically get asked as the first question, what about the cost of this? It's not cheap. It tends to be 1 to 2 orders faster than the DNS. It all depends on how much interface is in your computational volume relative to the rest of the volume. And with that, I'll stop and take questions. Thank you.
Okay, the talk is open for questions. Yes.
Very impressive, Marcus. I have one question. So when one derives the LES equations, usually one is tempted to go with the Smagorinsky approach, which is basically for low speed flows, one species, etc., no interfaces, so simplified. But if you derive the equations from first principles incorrectly, you always get differences between a filter term and a term computed as a function of the filter variables, the LES variables. So my question is, perhaps here you can get the same thing, which is only your filter term from what I can see. That may give you an additional, this may give you an additional leverage in terms of modeling.
Yeah.
Maybe you can use a smaller number of cells with just an improved model.
Maybe, hopefully, maybe.
Maybe.
I'll take that.
So that was very interesting. I'm a chemist, and I'm not used to thinking about surface tension in the context of springs, and so I thought that that was lovely. But I am used to thinking about it in terms of thermodynamics, and so I'm curious if you, and maybe this is related to your future work, if you have a good sense of the sensitivity of like the free energy of deformation with your spring constants that you're using, because I would think that that would also feed directly into like evaporation rates and all sorts of things like this.
Yes, so in a sense, right, I glossed over the entire thing. I said I have a constant sigma, which is if you inject into combusting devices with strong temperature fluctuation, that's not obviously the case. And now how can you do that? It's kind of hinted at with the evaporation. So what you would have to do is you take your mean LES filter thermodynamic properties. If you now go to the DNS scale, you could enhance that with fluctuations like we do with the velocity, perhaps to get variations locally, spatially in there. And then you have to account for, what is it, tangential surface tension, the term escapes me, variations in the surface tension inducing flow fields. But it's usually, that might not be that important in these high shear atomizers.
Okay, nice talk. I have a quick question. Do you include stochastic random fluctuations of the interface? How's it included there?
So no, not directly. Indirectly, yes, by the reconstruction of the velocity field. So we don't introduce additional fluctuations on the interface, only the ones that are generated by the SDF reconstructed DNS scale velocities. So we'll just let the interface evolve like that. So that's why there are all of the, well, it's not in the other movies, you have these small perturbations on there. The question is, how well are the velocities reconstructed? But they're not DNS velocity fields. We did a priori tests where we just used DNS velocity fields for the reconstruction, and they gave kind of similar results.
In the interest of time, I'm going to have just one final comment, which is the very fundamental importance of the subgrid models. And as you go into more complicated physics, the subgrid models have a very deep physics modeling aspect. And they're not just following some crank. You have to do new science to discover the correct subgrid model.
I tend to agree.
Thank you very much. And we'll move on to the next.